So what I'm going to do in the next few minutes is just to look at what are the impacts, health impacts of air pollution, how do we measure them, what are the issues in their measurement, what are the limitations, and how does it help in terms of mitigating air pollution and reducing the adverse health outcomes. So some of these questions I'll try and address. So I think all of you must have seen this many times, that 99% of districts in India have PM2.5 levels much above the WHO guideline. The WHO guideline says that it should be less than 10, but 99% of India has above 10. Then the National Ambient Air Quality Standards says that it should be less than 40. And that itself is also 60% higher. And most of the air pollution is in the Indo-Gangetic plain, starting all the way from Pakistan and ending in Bangladesh, much higher in parts of India, particularly near in and around Bihar and Uttar Pradesh. So if we were to write a headline for air pollution in terms of health outcomes, what would it be? So the annual population weighted mean exposure to ambient air pollution particulate matter 2.5 is around 90, close to 100. So we are saying the national standard is 40, but it's more than 2 times the national standard. So I already mentioned that the Indo-Gangetic plain has the highest exposure, and it's a combination of both indoor and ambient air pollution, which is outdoor air pollution. The proportion of people using solid fuels in India is around 50%, more than 50%, but that's coming down because of this use of liquefied gas for cooking. But many people still use this hybrid approach. They use this for eating water, but for cooking they use the conventional approach because people believe the tastes differ when they use gas versus the conventional fire. According to this state-level disease burden estimates, close to 1.25 million deaths are attributed to air pollution, of which nearly 0.7 million is due to ambient or outdoor air pollution, and around 0.5 million is due to indoor air pollution. So 60-40 is the ratio, 60% due to outdoor and around 40% due to indoor air pollution. But the biggest problem is that more than 50% of the deaths occur before the age of 70 years. So anything occurring before the age of 70 years is considered premature. If you take the deaths in the Western population below the age of 70 years, it's just around 20% or so, whereas in India it's more than 50%, and to a large extent contributed by air pollution. If you calculate the overall life expectancy, there's a loss of around 1.7 years in terms of life loss. So a child born today would lose around 2 years of life because of air pollution. Suppose you were to buy some magic wand who was supposed to eliminate air pollution, that child would gain 2 years of life. So that's the kind of calculation. Then there's another metric of measurement which epidemiologists and economists use, which is very difficult to understand. It's called the DALYs, which is disability adjusted life years. So it's a combination of the death and the number of years lived with disability. Right? Suppose somebody develops a disease at 35 years and is disabled with the disease, lives till 45 years, but the country's life expectancy is say 65 years. So the number of years of life lost plus the number of days or years lived with that disability is taken into account, and a combined metric is given, which is called the disability adjusted life years. So if you look at the disability adjusted life years contributed by air pollution and compared to tobacco, air pollution actually is much higher in terms of its contribution to lower respiratory infections, cardiovascular diseases, even ischemic heart disease, chronic obstructive lung disease, stroke. Across all the diseases, it appears to be higher than that caused by tobacco, because if you ask any doctor or any health professional, they tell you that tobacco is a very important cause of cardiovascular disease or lung disease. In terms of air pollution, some doctors will say it's bad for the lungs, but not many people will say it's bad for the heart, because that knowledge is not there. So the idea of this session is to actually impart that knowledge so that you can communicate it better to policymakers and others. So let's look at some of the chronic diseases linked to air pollution. The biggest link to air pollution is cardiovascular diseases, and cardiovascular diseases are comprises of the heart attacks or coronary artery disease that many of you know, the chest pain and angina and heart attacks. The second is gangrene. Then, of course, we have the chronic obstructive lung disease, and to some extent, a few cancers. So the others include heart failure, dementia, and cognitive impairment. But the risk factors of cardiovascular diseases are also influenced by air pollution, and these include hypertension, diabetes, and obesity. If you look at the cardiovascular disease prevalence and the incidence of cardiovascular disease, it's one of the highest in the world. Indians have a very high propensity to develop cardiovascular disease and diabetes. And the reasons that have been attributed are largely biological, but we have missed out on air pollution, and air pollution could be an important reason for increasing the risk for cardiovascular disease and diabetes. Now, how does this happen? There are multiple mechanisms by which cardiovascular disease can result from air pollution. So, you know, PM2.5, particulate matter 2.5 is extremely small. When you compare it to the diameter of the hair is around 70 microliter. So, you imagine this will be around 12 or 13 times smaller than a hair diameter. So, it's as small as that, and it can cross the alveolar blood barrier, which means that you breathe in, it goes to the deepest part of the lung, where we have what are called the terminal part of the lung is called the annulus, and it's just a simple cellular structure separated by blood on one side and air on the other side. So gas exchange takes place in that annulus, and this can cross that annulus and enter the blood. Once it enters the blood, it can damage the blood vessel. The lining of the blood vessel can get damaged. It can produce what is called as inflammation and produce various hormones which actually increase the risk for atherosclerosis, the formation of the waxy substance in the blood vessels, increase the risk for heart attack. It increases blood pressure because it makes the blood vessel stiff, and it can cause abnormalities in the heart rhythm, sometimes resulting in sudden death. In addition, it can cause metabolic abnormalities. In fact, the PM2.5 is considered as an endocrine disruptor, and it's believed that it can damage the pancreatic islets. Some of the cells in and around the abdomen, the fat cells, can get activated to become inflammatory cells. Inflammatory substances are released which can increase the atherosclerotic process. It can result in hypertension, arrhythmias or irregular beats of the heart, and it can cause reduced function of the heart muscle, which we call as renal dysfunction. All of which can result in ischemic heart disease, peripheral vascular disease, chronic heart failure, arrhythmias, and sudden death. So, but what is the evidence? These are all theoretical. You need to prove that this actually happens. So, what's the evidence base in India? So, most studies somewhat deficient in exposure, but I think there's a lot of data on exposure. You have disparate data come from multiple sources. You have exposure data, but in terms of outcome assessment, in terms of the linkage of the exposure to outcome, it's not very robust. Most studies are on suspended particulate matter and PM10. Right? PM2.5 monitors are very far and few in this country. There is little to no examination of cardiometabolic diseases, which we spoke about. No examination of prenatal and early childhood exposures. It's one of our colleagues in Bangalore is studying that, looking at PM2.5 levels and pregnancy outcomes and following up the kids who are born to look at cognitive impairment. So subtle cognitive impairment is known to occur, and you need to prove that. The neurodevelopmental effects. Most studies are either what are called as interrupted time series, that year on year you measure, look at deaths in that particular year compared to the next year, which is a good way of starting, but not a great way of showing causality, that air pollution causes certain disease. The second is cross-section, will explain that a little bit later, and the role of long-term exposure is not known. We also do not have data on microenvironmental profiles. Like I came from Bangalore airport to this place, and I spent almost 1.5 hours in the car. How much am I exposed to PM2.5 just by sitting in the car? We don't have that kind of data. If people are doing that every day for 2 hours in the morning and 2 hours in the evening, what would be the exposure of PM2.5? That's not known. So we require data on that. So let's look at how we relate an exposure to cause. Now exposure here is PM2.5 or air pollution to an outcome, let's say heart attack. How do we do that? So essentially we use this simple algorithm. There is an exposure which is related to the outcome. So the true relationship will come only if you exclude what are called as confounders. There are other factors that can cause. Tobacco smoke can cause, diabetes can cause heart attack, bad cholesterol in the blood can cause heart attack. Now you have to adjust for all of that, and then if there is any residual effect that's remaining, then you can say that there is a relationship. So there are various research methods that are used to look at this relationship. So what are the studies that are possible? There are various studies that are possible. Now let me explain in a simple way three major designs that are used in epidemiology to study relationship. One we call is cross-sectional, then we have case control, and the third is cohort. All these are called observational studies because we are not doing any intervention here. We are observing people, we are collecting the exposure data, we are collecting the outcome and relating it. So they are observational studies in that sense, right? Now let's look at cross-sectional. So what exactly are we trying to do with gathering data on exposure, gathering data on outcome, and relating exposure to outcome. In a cross-sectional design, we collect data on exposure and outcome at the same time, right? Like for example, I want to know what's the relationship of prevalence of heart attacks in prevalence of heart disease in Bangalore, and what is the level of PM2.5 over 1 year period. I look at the average PM2.5 levels and look at the prevalence of heart disease. But there is a problem with this. What do you think of the problems? Anybody? What is the problem with the cross-sectional design? It's an easy design to do. You can just go and do it, but there is a problem. What is the problem? Exactly. You cannot account for what happened in the past. You cannot account for people who have died because air pollution may actually cause death and you're missing and you're actually estimating something which is mild. So that's a problem, right? So then they said we'll have to look at other designs other than cross-sectional. Cross-sectional will give you a feeling that okay, there is a relationship, but we don't know what is the nature of the relationship. Is it causal or is it something else? So in epidemiological studies, the next level is what we call as case control. Particularly for air pollution, it's going to be difficult. In case control disease, what we do is, suppose somebody has got a heart attack, we won't count them. And we get another control who doesn't have a heart attack, is a normal person. And then we interview them and ask them, okay, were you exposed to air pollution? The fellow with the heart attack will say, yeah, I had. And somebody who's a control will say, I don't think so. I am perfectly all right, I don't think so. So you see there is an inherent bias and it's very difficult to do a case control study in terms of air pollution. So the next best design is what we call as a longitudinal study, the cohort study. So here we start with a bunch of people who are normal, follow them up for a long period of time and look at in future whether they develop disease or not, right? So here we are starting with without any bias, we are starting with a group of people, we are following them up over 10 years or 5 years period, looking at what happens in terms of the air pollution, PM2.5, using robust methods of analysis, etc., and then relating it to. So it's a kind of design that is considered good. So if you have data from longitudinal data sets, then your data is considered little robust. Unfortunately, there are very few longitudinal studies in India, right? Now let's go back to the other design. So we spoke about cross-sectional, we spoke about case control, and we spoke about longitudinal. But for policy making, there are other designs that are very important. You cannot wait for 10 years to show policymakers to say that, okay, air pollution causes heart disease. You require something else, you want to do it rapidly. So for us, we have databases. The CPCB will have some database. You can get database from satellites. You can have emission inventory data. So from that data and from other health data that have been gathered across every year, you can look at the change in mortality or change in heart attack over the last 5 years and say, okay, over the last 5 years compared to 2014, in 2019, the number of people who have died due to heart attacks is higher. And simultaneously, there has been an increase in the level of PM2.5 year on year, and therefore we are saying that it is likely that air pollution is causing this extra heart attacks. Suppose there were 100 heart attacks in 2014, today there are 150 heart attacks. You would say there is a 50% increase. And this increase could be due to air pollution. There could be other reasons also. People who would have started smoking, for example. Or the oil prices would have come down and people started using a lot of oil in their cooking. Or energy dense foods might have become cheaper. So you need to adjust for all those things. Then see if there is a real increase, and then you would say, okay, there is a 10% increase, and that 10% increase could be because of air pollution. So this is called the time series. Some people call it as interrupted time series because there is an interruption between the every time you measure. Then there are trials. Trials are required to see, like we advocate masks, and we look at N95, N99 masks. How do you know that they really work? Are they really helpful? So you would get people with some disease like heart failure or coronary artery disease and tell them that whenever you go out, please use the mask. So you do a trial, and a bunch of them would get that mask, bunch of them others would get a simple mask with no effect, and then you would see there's a difference ultimately in their mortality, death, the repeat heart attack, and so on. So that's a trial. Then you have case studies, because you are required to provide policymakers with clear case studies. A case study of a simple intervention which was done. Let us say Delhi is a great example when they did this alternate day, allowing vehicles by even and odd numbers on alternate days. So that could form a case study. You could look at what happened in that time, whether they gave 2.5 levels gave. So you create a case study and provide it to policymakers. That's one example. Then there is a policy analysis. Suppose there is for example, the Supreme Court banned diesel vehicles in 2000 for commercial purposes, and said all commercial vehicles should have LPG-driven vehicles. They also moved polluting industries out of Delhi and then sent them out to the peripheries. Now that policy, it did make a big change in terms of PM2.5. So that's a policy analysis, right? Then systematic reviews, because not all of us can do all the studies. There will be studies published everywhere in the world. You pool them in a way where they are comparable, and then get a result. That's called meta-analysis or systematic reviews. Then of course you will require, sometimes you have to give policymakers the cost. You would say that, look, we are going to lose $25 trillion by 10 years if you don't do anything about air pollution. There are various methods to estimate the cost, so it's not really required to go into details, but that's one method. And cost effectiveness, of course, is there's an intervention, reduce the cost of this air pollution related deaths, reduce the cost of healthcare, that way you can pose your question. So for all this you require data sources, and most people use secondary data sources because collecting primary data is very difficult. It takes a lot of time, it takes a lot of effort. You have to collect it in the right way, and it also requires a lot of manpower. So people rely on secondary databases. So you have the National Family Health Survey, the District Lifestyle Health Survey, and the National Sample Survey Organization. There are hospital data and then research data. So these data are freely available. So if anybody wants to play around with the data, you can actually look at, you can get the PM2.5 levels or PM10 levels in Bangalore. Look at the DLHS data of Bangalore and see whether there's been any change over years. So one could do it for a PhD or for a postdoc or for policy analysis. Similarly, we have hospital data, whether there's been a change in emergency admissions because of heart attacks or asthma or chronic obstructive lung disease. And research data, because nowadays we have open source applications. Most of the funding organizations want the research data to be brought to the open source, and people can use those kind of data. So I'll stop here before moving on and ask if there are any questions, anything that you did not understand. You can, if I've gone past, you can tell me and ask questions. Any questions? Yeah.
The cost of air pollution
in June 30th, 2019 was 50. And we calculate number of people who had a heart attack or died because of something or had an exacerbation of lung disease, asthmatic attack. So you pool all together all that and calculate the cost, right? The cost of the illness. And say because of this, the cost of illness was this much. So that's what is the cost of air pollution. Right. It's a good question. It depends on the resources that we have. Current resources allow us to, because PM 2.5 is supposed to represent most of the air pollution things. You of course require black carbon estimation, you require NOx, all that you require. But the cost is going to be prohibitively high. And for simple messaging purposes, everybody knows PM 2.5, and therefore we use that. I mean, the other things that you mentioned have a correlation to PM 2.5 levels. As PM 2.5 levels go up, SOx and NOx also will go up.
Higher level of emission norms in terms of vehicle, as well as, for example, BS6. Oil industry has put around 40,000 crores. And if you really look at the IRR payback, it is not so good.
Yeah.
So only way where we can convince is through this economic process.
It's called an econometric analysis. So
is it easy to access, or is there access for anonymized hospital data?
Yeah, I mean, you have to get ethics clearance, and the data has to be truly anonymized. So it's not supposed to trace back the patient from that data.
So an individual can't really access that.
No, individuals also can. I mean, through an institution you can access.
Okay. And are the institutions doing it? I'm sure.
One of my colleagues is actually working on lead levels.
I would consider air pollution as a significant factor, or environmental pollution in general as a significant factor in the decision making.
The short answer is no. But the long answer is, let me go back to my experience as a medical student, which happened close to 40 years back. And then there was nothing on air pollution. Nothing on pollution, nothing on air pollution, nothing on toxins. But there were, toxins were related to poisons, but nothing in this way things were looked at. Then, now doctors are not aware, nobody is going to ask questions on air pollution or how it is. So we have created a platform, I'm going to talk about it. Next. So if there are no more questions, let me move on. So in terms of, you also need to define what condition you are going to measure. You can't say that I am going to measure heart disease. Heart disease is a big basket of things. So you have to exactly define, because for communication purposes, a heart disease by you should be the same as the heart disease by somebody else. So we need those definitions. And generally for heart disease, we use this. For fast heart attack, we use ECG and certain ECG criteria. An angiography or angioplasty, you look at medical records. For gangrene and disease of the peripheries, you look at medical records, gangrene and amputations. For heart failure, we look at medical records and symptoms. For chronic heart disease, is angina, medical records and symptoms. For stroke, medical records, symptoms and some evidence of stroke. And risk factors, we look at hypertension, diabetes. I went through this fast, but the slides are there, so you can have a look at it at relation, right? So you have to have a clear-cut indicator of how to measure. Only then your findings will be credible. You cannot ask a research question saying that does heart disease increase because of air pollution? The question has to be framed in a very, very specific way. Does air pollution as measured by ambient PM 2.5 levels using whatever relate or determine the occurrence of acute myocardial infarction or heart attack as defined by the universal diagnostic criteria, so on and so forth, right? So you have to define your research question in a very specific. So let me show you some examples. I mean, these are data that have emerged very recently. A lot of data have come from China, and there are 3 studies, one from Taiwan and 2 from China, which shows that for every 10 microgram per cubic meter increase in PM 2.5, the blood pressure or risk of hypertension increases by 3 to 14%. Right? So if you just take the city of Delhi and you start at 10 and say 10 is normal, city of Delhi has 90 or 100, that means the blood pressure of the population and the residents of Delhi should be at least 30 millimeters higher, use the higher value, or maybe 10 millimeters higher. And that's actually been shown. Between around 1942, the average blood pressure in India, systolic blood pressure, was 112. Then in the 1980s, it was around 122. 1997, these are data from the WHO, it was around 130. Current blood pressure, mean blood pressure in Delhi population is 132. So there's been a clear 20 millimeters increase. It could have been other reasons, lifestyle, increased alcohol consumption, low physical activity, but air pollution could be one of them. And this has been shown in the Chinese studies. But there is one problem in this. All these are cross-section. Right? There are not many longitudinal studies in the world. Linking here, there are longitudinal studies, but not many in terms of air pollution. So, what we did was, we created a longitudinal study, and I'm going to talk about it a little bit later, but in terms of air pollution, we are doing the following things: research, capacity building, policy making, and advocacy creating awareness. So we assembled a cohort in the cities of Delhi and Chennai starting in the year 2010. So we have a total sample of around 19,000 individuals. They have been followed for 8 years. They are representative of these two cities of Delhi and Chennai. They are carefully phenotyped. That means we know about all their medical illnesses, the diseases that they have, and geocoded because we know their location. So we want to get exact PM 2.5 levels. I'll come to that. And we have blood samples stored in the long term to look at many of the risk factors. So this is how we are doing the study. The baseline was conducted in 2010, 2011, collected data including bloods. In 12, we collect data of hospital admissions and other things. So in 2014, we again collect all the data and so on. So it continues every alternate year, and we have a very rich data of these. So in terms of air pollution and cardiometabolic diseases, we wanted to develop a model to estimate ambient air exposure to air pollution, estimate association between exposure to air pollution, temperature, cardiometabolic risk factors and diseases in built environment, examine DNA methylation because air pollution is believed to cause alteration in the DNA. It methylates the DNA. So we want to do that, and association between air pollution and vitamin D levels. One of the very surprising things amongst Indians is vitamin D levels are very, very low. And actually don't require anything for vitamin D because sunlight. The question is whether because of air pollution the ultraviolet rays are not getting in and not helping in the conversion of the skin substrate to vitamin D. So we are going to do that. Now in terms of what we have done in terms of the model, the other thing right now is when we estimate air pollution in most places it's a 10 kilometer into 10 kilometer grid. It's as wide as that. Our studies show that even within a matter of 2-3 kilometers is a big difference because of greenery, because of the way the buildings are constructed, traffic density, and so on. So we are creating a grid of 1 square kilometer to 1 square kilometer. For the city of Delhi, we created 1,635 grids over a 7-year period, which was around 2,557 days, and there were close to 4 million observations, and the area was 1,480 to 1,500 square kilometers. So unlike most other studies which takes data from one given source, we are using 5 sources. So we are getting pollutant levels from stations, PM 2.5 and PM 10. We get data from the satellite, looking at aerosol optical depth, vegetation index, ultraviolet emissions in active fires, emission inventory data. And the weather data is very important because wind speed, rain, all that can make a big difference. So we have data on every day for those last 7 years. And land use, because land use can make a big difference. Greenery, PM 2.5 levels can be lower. So based on this, and using machine learning and artificial intelligence techniques, we have calculated the PM 2.5 levels. We can give the data every day, but this is month-wise data from 2010 to 2016. And you can see in the latter years, from 2014 onwards, the red in the map keeps on increasing. And you also will notice, starting from October onwards, you will start appearing red, seeing the red areas in the map, highest in the month of December and January, which is known. I mean, you don't need to study, but it gives a clear indication when it starts, right? But the problem is, when people report air pollution in Delhi, they report it for the whole of Delhi. But there is a huge difference between these two areas, this area and this area, this area and this area. Why does it happen? Because of multiple reasons, traffic, greenery, and so on. So that's why we created this 1 kilometer to 1 kilometer grid. Now, how does it help us to look at outcomes? we have the data of these 90,000 people, we followed them up, and we know that we excluded patients who had hypertension, nuclear hypertension at the baseline, and we just collected the normal people who did not have any disease, and followed them up, and found that nearly close to 3,300 individuals developed hypertension over a period of 7 years. And what we did was we looked at what happens for every 25 microgram increase in PM2.5. So the chances of developing hypertension increased 2.5 times at the basic minimum, 2.5 to 3 times. And as it also had an interaction with body weight. If people were obese, then their blood pressure levels were likely to be higher because of their pollution. I mean, this was after adjustment for several other factors which actually can increase blood pressure. So clearly we are showing a relationship that development of hypertension is linked to air pollution. This is under publication. So we have types of chronic exposure adjusting for age, gender, time, occupation, education, household. All these are adjusted, and despite that, there is a 2.5 to 3 times increase in the risk of blood pressure for every 25 to 30 microgram increase in PM2.5 levels. We are also looking at personal monitoring of individuals because, as I mentioned, that we don't have the microenvironment profile. People travel, people cook at home, and those kind of things. So we are looking at personal monitoring and developing a PM2.5 exposure profiles over a 24-hour period. This is being done both in the summer and winter, and it's an ongoing study. The other projects is in Bangalore, we are looking at aviation and indoor air pollution in pregnancy on the risk of low birth weight and ensuing effects in infants. It's called the Apple study, and it's based in an urban slum in Bangalore where solid fuel use is high, and air stress is the impact of air pollution on low birth weight infants. Exile is a trial of a clean cook stove in an urban slum of Bangalore, and then we are also looking at a mixed methods research to look at the experience of asthmatic kids during days when the pollution levels are very high. What happens to them? Then we are looking at health impact assessment. We have thermal power plants. It's completed and it's been reported. Economic costs of air pollution in India based on literature level modeling and data analysis. And impacts on environmental burden of the disease, the economy and human capital. You were asking about it. So with even environmental program at Boston College, we are working on this. So these are some of the ways we are trying to link air pollution to health outcomes, right? At this point, again, I can stop and take some questions.
The pollution exposure on low birth weight.
Yeah.
So, can you just give a little more details?
So what their levels of indoor air pollution, because many of these are low socioeconomic status families, indoor air pollution because of cooking practices, and relating it to the birth weight. So the hypothesis here is that higher the level of indoor air pollution combined with ambient air pollution, the birth weight of the kids will be lower. Okay?
So that could be also because of malnutrition.
Of course, lower nourish. You stratify according to that and do an analysis. But the simpler way of doing is to just put it into a logistic regression. So you put a variable for that, for the nutrition number, which is measured. Several short-term courses conducted by PHFI with various people coming from various institutions. I think even somebody from CSTEP was also there attending one of our courses. So more than 200 beneficiaries have been trained from 25 institutes and organizations. And most of them are from public health or medical background, master's level or higher training. So these are some photographs of those sessions. And we are also training people to become leaders in the area of environmental health. So we have actually advertised, and I'm surprised that we are not getting candidates because this is a fully funded MPH program in Harvard. Fully funded 1.5 to 2 years program. We are not getting people actually. So if anybody is interested, please write. Then we have said so far 7 people, and we are looking at several advanced level statistical analysis such as mediation analysis, exposure modeling, exposure assessment, environmental epidemiology, and econometrics. Then in terms of creating awareness and advocacy, we have created what is called as a health platform. Specific aim is to engage the health sector and build their capacity in terms of looking at air pollution, because doctors are the most powerful voice of the community, and they have a connection to policymakers. They just tell them. So, but for that they need to be empowered in terms of how to convey the message. Air pollution monitoring, policy and advocacy, understanding knowledge and attitude and practice of health practitioners towards health effects of air pollution in cities, and the roadmap to achieve nationally agreed air quality standards. So this platform has around 7,000 healthcare institutions in India, and the roadmap has also been done to understand the process of establishment of national agreed air quality standards, understanding the implementation of these standards globally across states and nationally, understanding the role of health in policy design and implementation, and understanding the barriers and challenges in implementation. So we are also creating this network of hospitals which measure air pollution levels using low-cost monitoring. Unfortunately, the low-cost monitors have a big problem; they get flogged. So we are looking at alternate ways of doing this, but we had put in around 15 air pollution monitors all across the country in places where there is no measurement of PM2.5. And there's a doctor study, the results also it's been compiled, we're writing the paper, looking at the understanding and knowledge and awareness of doctors about health impacts of air pollution. And the question is whether doctors communicate concerns regarding air pollution to these patients, because I've seen cardiologists discharging patients with heart failure who can actually deteriorate at very high levels of 2.5, and doctors are not talking about prevention to them, because it's very important to talk about prevention to heart failure patients. Lack of awareness, yes, exactly. And this air pollution feature as a priority within the health community. So these are some of the questions we are trying to address. Then there's so you need to provide evidence for policies and good evidence base. So studies on health economic effects of long-term exposures to air pollution is needed. Studies on comparable design conducted across various sites, because we showed Delhi and Chennai, but we required to look at other parts of India. Economic effects of air pollution in the Indian context. Somebody asked this question, I think we need that data. The role of socioeconomic disparities and development of the evidence base in Tier 2 and Tier 3 cities in alignment with national health programs and priorities. So I'll leave you with this quote, but we have quite a bit of time, actually 15 minutes more. Either we can break now or you can ask more questions. That you need to understand the statistics. Like if you understand,
how easy is it to do?
It is easy to do. I mean, statistically, it is easy to do. Like just a simple explanation. If you go back to your 10th, 11th standard or 12th standard mathematics, it's based on the line of equation of the line. How is the slope of the line determined? It is y equals ax plus b. Now we can plug in that x, and b is a constant. You can plug in that x, and x can determine what is y. Now in a multifactorial analysis, where there are 10 things, it will become x1 plus x2 plus x3 plus b, right? So you put that in your equation. Okay.
Like an independent organization like CSTEP or any other think tanks.
And collection of any health outcome data, you require ethics clearance. For secondary data, you might not require, but it is also good to inform. It's a good practice to inform your ethics committee that you are collecting data from secondary sources. So for that, the level of clearance is, rigor is not going to be very high. But if you are going to talk to even somebody on the roadside and asking 2 questions, let's say, are you aware of air pollution, have been affected by air pollution? Even for that, you will require ethics clearance. So it's important to constitute an ethics committee within your organization.
30 by 30 kilometers for 1 year, and then I correlated with the eye irritation data obtained from hospital data. So I could not find any correlation. Plus 3 lakh also I did, but we could not get any correlation from the black carbon data with the eye irritation. So in that case, what would have been the reason?
So when you look at that, will determine whether your results, when you get a certain result, you have to ask 4 questions. The first question is it a true result? Is it true? Is it a true relationship? The second question is it by chance? The third is there a compound, is something else doing this? And fourth is there a bias in the way I have collected the data? Once you answer those three questions and say, okay, there's no bias, there's no confounding, there's no, what is the third one which I mentioned? There's no chance, then I know it's a true result. Now the other problem with the kind of study that you are saying is to look at what is called as the power of the study. 30 kilometers is a large area. You don't have that kind of concentrated effort because the eye irritation may be happening only in a certain area. Because it's so widespread, it gets diffused. So the power is low in that particular situation. So there are statistical methods to calculate the power of the study. Sometimes you may get a false positive result. Even when there is nothing, you get a false positive result. That happens generally in smaller sample sizes. So you have to adjust for all those.
Air pollution, like a person is not directly exposed to the air pollution, but he has, like, suppose nowadays like animals and other things also, they get exposed to the air pollution, and for them also some health problem comes. And when person like especially a non-vegetarian or thing, he consumes those animals, or you can just take example of cow who gives us milk. And in some studies like I work more on water, but there we just found that the presence of heavy metals and other things in the cow's milk, and that when we consume it comes into our body. So same way, is there something is happening with the air pollution? Some studies are going towards that area.
So we don't have to invoke an indirect result like in foods. Not necessarily non-vegetarian food, even vegetarian food can have toxins, and they can get embedded there. We have done a study looking at residues of DDT in the blood in the same cohort and looked at whether it causes diabetes.